Okay, here we go. Probably want to pause the video here and there to take some notes, but we've got this function x squared times the square root of x plus 2. Here's a picture that depicts what's happening. This blue graph is the graph of the original function. The green dashed line is actually the graph of the first derivative, and the red dashed line is the graph of the second derivative. And the point where those dashed lines cross the x-axis are going to be critical numbers and hypercritical numbers for finding relative maximums and minimums and inflection points. As far as the domain goes, when you take the square root of an expression, that expression has to be greater than or equal to 0. So this is all you have to do to find the domain. Say x plus 2 must be greater than or equal to 0. So x is greater than or equal to -2, and you can see that's where the graph starts right here and goes to the right. And this is set builder notation for specifying the domain. Set of all numbers x such that x is greater than or equal to -2, comma x is an element of the real numbers. That's supposed to be the real number symbol. Okay, so the question is, how do we get these critical numbers? Well, we first have to find the first derivative and set it equal to 0 to find the critical numbers. My suggestion is to use the product rule. So we'll take the first function times the derivative of the second. When we do take the derivative of the second, you could put a parentheses right here to say I use the chain rule. The derivative of the inside is just a 1 though. Plus the second function times the derivative of the first. The derivative of the first is 2x. If we rewrite it in radical form with positive exponents, this is the first derivative right here. And to find the critical numbers, we want to know when does that equal 0? When is the slope of the tangent line equal to 0? So the way to solve this equation is probably to multiply every term by 2 times the square root of x plus 2 to clear the equation of fractions. And we just get an x squared for the first term. 2 times the 2x is 4x, and the radical times itself is just on the radicand. And I'll let you pause and take some notes here, but there's your critical numbers, -8/5 and 0. So you draw a little number line, can't go to the left of -2. Find f prime of a test number in each interval. So like f prime of -1.8. I did it right here on Desmos. That's a positive number, so the original function is increasing. In this second interval, I picked the number -1. F prime of -1 is negative, so the original function is decreasing. And to the right of 0, the first derivative is always positive, so increasing. So the intervals of decrease are from -1.6 to 0, from the relative increase from -2 to -1.6, and from 0 to infinity. You can use interval notation if you want to specify those intervals. And let's see, what else did we have? So we found the domains of increase. Oh, so we had a relative maximum at this point right here because we went from increase to decrease. So that value right there generates a max. And the 0 generates a min. And you can see from the graph that's the case. We have a horizontal tangent line here, horizontal tangent line here, relative max, relative min at 0, 0. Now, to get the point of inflection, you need the second derivative. This gets a little ugly, but here's the first derivative. So you could rewrite this with the x plus 2 in the numerator with a exponent of -1/2 and use the product rule, but I went ahead and used the quotient rule for this first term. So denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. I did the derivative of the denominator off on scratch paper, and the 2 and the 1/2 cancel out, all over the denominator squared. And then for this term, use the product rule. First function times the derivative of the second plus the second times the derivative of the first. And then if you simplify that a little bit, get 4x times the square root of x plus 2 minus x squared over the square root of x plus 2 all over 4 times the quantity x plus 2. What did I do to this term to get to here? What I did was multiply numerator and denominator of the big fraction by the square root of x plus 2. So we have a complex fraction. I multiplied by the square root of x plus 2 to turn it into a simple fraction, and that's how I got to here. And then this term simplifies to the 2's cancel, so x over the square root of x plus 2, 2 times the square root of x plus 2. And we want to know, when does this mess equal 0? Well, I got to maybe simplify that. 4x squared plus 8x minus x squared is 3x squared plus 8x. What I did is multiply every term of this equation by this denominator right here, because that's the LCD of all these two denominators. And I'll let you figure out what happened here. It's just multiplying through by the LCD, combining similar terms, simplifying and combining similar terms. You get this quadratic equation. Probably simplest to solve that by using the quadratic formula, where A equals 15, B equals 48, C equals 32. Turns out to be quite a mess. This is one of the roots of that quadratic equation. And this is another root, but this is not in the domain. So this cannot be a point of inflection. And if we put these points, or this point, on a number line like I did up here, and apply the test for concavity, negative 0.468, this interval from negative 2 to here, I could pick a test number like negative 1. F double prime of negative 1 is negative. So the original function, since negative, think down. And then to the right of negative 9.468, like 0, F double prime of 0 is positive. Think smiley face. Since the concavity changed from down to up, this is a point of inflection. Okay, and you could put negative 9.468 into the original function to get the y coordinate. That y coordinate is, it looks like 0.91997 approximately. Okay, there you go. Hope that helped. If you have any questions, post a comment.